Here we are still interested in Markov jump processes, but discuss the description in terms of something called paths. Okay? And there's nothing really difficult here, but I would say that notations are a bit heavy. So I want to summarize them carefully here. Okay, again, we consider an arbitrary Markov jump process with time-dependent transition rates, about phase omega t, which is simply the collection of all these transition rates with j equal not k. And the escape rate is given by this, we sum over k. And again, I denote by omega tilde the collection of all the transition rates for any t in this time interval. Now tau is the final time, and I'm mainly interested in time from this time interval in this part. Okay. And let me first define a new quantity called the staying probability, p tilde, and it depends on the state j and t prime satisfying this inequality. It is the probability that the system is always in state j throughout the time interval from t to t prime, with the condition that the system is in j at initial time t. Okay, this means that when t prime equals t, then this must be 1. Okay, it's here. And as t prime increases from t, then this gradually decreases because there is escape from the state j, and this escape is described by this differential equation, right? Okay, and this is the escape rate. And if suppose that this lambda is time independent, then this is one of the simplest ordinary differential equations you can think about, and the solution is simply the exponential decay, like this, right? So in general, if this lambda is time dependent, you have to have integration here. But anyway, this is basically the exponential decay. Okay, this is the staying probability. Now I discussed the important notion of a path. And so suppose that you run a Markov jump process. Then, of course, you do not immediately get p of t, right? What you will get, or what you will see, is a history which looks like this. The system, for example, starts with some state j0, and at some time it jumps to j1, and at some time it jumps to j2, and so on. There are 4 jumps in this case, and you end up at state j4. And this is the end, the final time. Okay, and so here's the general description. So gamma, in general, gamma is a path or history in the time interval from 0 to tau, and which connects the state gamma init and gamma final with n jumps. And n can be 0, 1, 2, ... any integer which is larger or equal to 0. Okay, and here's the general description of gamma, a path. It's a collection of, first of all, the list of sites, the list of states that gamma visits. So J0, J1, J3, J4, there are n plus 1 states. And here is the list of time at which this jump takes place. So T1, T2, Tn. And of course, this time, T1, T2 must obey this, must be ordered like this. And also it's convenient to denote 0 as T0 and tau as Tn plus 1. Okay, and in this case, we say that the mth jump takes place at Tn, and in this jump, the system jumps from the state Jm minus 1 to Jm. Okay, anyway, this tells you everything. And this is a slight abuse of notation, but by using the same gamma, I denote by gamma t a function of time, which describes this graph. Okay, and yeah, if t is within this time interval, it takes value like this. And this I took open interval, open end here, and closed end here, but it doesn't mean anything. This is just a convention, and I just said like this. Okay, so anyway, this denotes a discontinuous function of a path. And of course, if you run your Markov jump process, next time you get a different path. Okay, so every time you get some path, and there is probability density associated with path. And before that, I want to discuss the quantity called the transition probability density of path gamma. This is basically the probability density for a path when the initial state is fixed at J0. But anyway, I called it the transition probability density. Okay, so it's T, and it depends on, of course, on omega tilde, the collection of transition rates, and it's defined like this. So what is this? Well, first of course it's a function of gamma. It starts from J0, and here's the staying probability that the system will always stay in J0 from throughout this interval. And then here's the transition rate corresponding to this jump. And then we have staying probability for this, jump rate for this, and so on. And finally, we have this jump rate for this final jump, and the staying probability from this final jump moment to the final time. And of course, you can write this compactly in this way. And yes, in this note, in this description, this convention is very important. Good. Now, in order to write down the probability density for a path, we need to specify the initial distribution. So let P0 be an arbitrary initial probability distribution. So we choose it and fix it. And then we can write down the probability density of a path gamma, which is this. Well, it's simply the product of this initial distribution, but we replace this J by J0 or gamma init. They are the same thing. And it's a product of this and this transition probability density. Okay. And so the definition of this T is here. So this is the whole thing. What does this mean? Well, it simply tells you what happens in this Markov jump process. First of all, you choose your initial state according to this probability distribution P0. Okay, so this is your initial state. This is a probability that you get this initial state. And then this is a probability that you are always at J0 from 0 to T1. And this is a rate, hopping rate that you jump from J0 to J1 and hopping rate, and finally the staying probability. So you will see that this is a probability density associated with a path gamma. I said probability density because although these J0, J1 states are discrete, this jumping time T1, T, these are continuous. So this must be some rate, probability density. Okay, probability density. Good. So since this is a probability density for a path, then you plug this in here, and if you sum this over all possible paths gamma, then by normalization condition you must get 1. What do you mean by summing over all possible paths? Well, that's simple, and it's written here. First of all, you sum over n, and n is the number of jumps. And as I said, it starts with 0 and can be any positive or 0 integer. Okay, and then you sum over all states that this path visits. So G0, J1, Jn are summed from 1 to omega. But recall that we do not consider a jump from J2 itself. Whenever we consider a jump, we assume that J and K are not the same. So this sum is not really free, and we have one constraint that Jm minus 1 is not equal to Jm. So this prime indicates that we have this constraint. Of course, I could have written this constraint explicitly here, but I thought it's easier to use this physicist notation, indicating constraint with this prime. Okay, then we still need to sum over all t's, but recall that this time t1, t2 must satisfy this inequality. So you do this integration. First of all, t1 is simply integrated from 0 to tau. t2 is integrated from t1 to tau. t3 from t2 to tau. And so by you doing this, these t's are naturally ordered in this way. So this realizes the sum over all paths, and you should get this normalization condition. Okay, and okay, so without this is 1. But if you plug in something, in this case we put Kronecker delta here. And what is this? Well, gamma of t. Gamma of t is simply the path described as a function of t, time. So gamma of t, of course, means the state at time t. So this Kronecker delta picks up the path in which gamma of t, state at time t, is exactly equal to j. And so this is 0, 1, and you simply sum over this. And then, of course, what you should get is a probability that the system is in the state j at time t. What is this? Well, this must be the solution of the master equation starting from this initial state. We start from this initial state and solve the master equation to get p of t. And yes, this pjt is simply an element, a component of this p of t. Okay, so if we consider the meaning of this, then the identity 3 or 5, I think, are obvious. Here, t is, of course, between 0 and tau. And they are obvious, but of course, I mean, if you want to be rigorous, you need to prove this. And I won't go into details of the proof of these identities because they are more or less trivial. And if you think they are trivial, you can just go ahead. But if you want to prove them, yes, it's good. So why don't you? So here, I will just give you a brief idea, hint about how to prove these identities. Okay, and probably there are several strategies, but one nice strategy is to, first of all, start from this path description and get the master equation, okay? The standard description, the master equation. Then you will see that the two descriptions are equivalent, and that leads to the proof of this and this, if you think a little bit. So here's the strategy of getting the master equation out of path description. Okay, and first of all, let gamma be any path for the time interval from 0 to tau. Okay, and I denote the final state as j. And then I consider a path gamma prime, which is a path on this larger time interval. Oh, delta tau is a small positive number, small positive quantity. So this is a larger time interval, but with the constraint that which gamma prime is equal to gamma for this smaller time interval. So yeah, this is clearly. So first we consider this time interval. So this is simply the path gamma. Okay, and then we extended time interval to tau plus delta tau. And so here are two gamma primes that you get from the same gamma here. Now we look at the probability density for the larger path gamma prime, and then by definition it's written like this. So this is the initial distribution, and this is a transition probability density. Okay, but this is a bit abbreviated notation, and this is the probability, transition probability density from time for the time interval 0 to tau plus delta tau. Okay, and now we want to rewrite this as a product of the probability density for gamma, okay, times some correction, some extra term. Okay, and of course the probability density for gamma is written in this way. Again, this is a bit abbreviated notation. This is a transition probability density for the time interval from 0 to tau. Okay, this one is from time 0 to tau plus delta tau. Okay. Anyway, we want to decompose this like this. And to do this, we have to classify the situation. And first of all, this must be the most common situation. Suppose that nothing happens, like in this situation, nothing happens after this time. Okay, and then in this case, we want to consider this. So let's go back, and let's say that this is gamma prime, and then this tau should be tau plus delta tau. Good. And we assume that nothing happens between tau and tau plus delta tau. So it means that this Tn is less than tau. Okay. So actually I have written it here like this. Okay, so it corresponds to the staying probability in this interval. Now I claim that if there are if t double prime and t prime are ordered like this, then this staying probability from t to t prime is decomposed into the staying probability from here to here and staying probability from here to here. Oh, this is very simple. You get this immediately from this integral expression, or from the meaning. This is clear. Okay, so by using this, this is a staying probability for this interval, but it can be decomposed into the staying probability for this interval and the staying probability for this interval. Okay, and look, this is for time less than tau. So this is actually what you have in here. Okay, what do you have in here? So what remains is this. What remains is this. So in this case of no jumps, then this precisely becomes this times this. Now we look at the contribution in the lowest order of delta tau. Then the lowest order is 1. So the next lowest is minus delta tau times the escape rate and higher order. Okay. That is the case with no jumps, and suppose that there is exactly one jump between tau and tau plus delta tau. Okay, and now in this case, again, we have the staying probability for this time interval, but it can be decomposed into staying probability of here, which is contained in here, and the remaining staying probability, which is this, from tau to this is TF, the final jump time, and then the jump rate at this time, and this is the staying probability from here to here. Now, in the lowest order, in delta tau, this is basically 1. This is basically 1. And you can replace TF by tau. So what you get is this. This is just a rate. And with this rate, there is a jump at some TF between tau and tau plus delta tau. So actually, this describes order delta tau effect because of this time interval. And now, of course, there are cases where there are many more than one jump, 2 jumps, 3 jumps in case those cases, but you can easily convince yourself that this gives you higher order in delta tau. So in the lowest order in delta tau, what you have to consider are only these 2 cases, but then you can neglect this. Okay. Then from this, you get, for example, the normalization condition, because if you sum over all these rates, then you just multiply this by delta tau, and you sum over k, and then what you get is precisely this. So if you sum over these in weights, you get 1. And actually, this is how you prove this normalization condition. Okay, and also you see that this is basically basic description of the this Markov jump process itself. This tells you that there is within small time interval delta tau, there is a jump from j to k with probability omega j to k times delta tau. And so this is nothing but the definition of the process itself. So from this, you can derive the master equation. And from the master equation, you can justify this relation. Okay, so that is how you prove these identities. But anyway, if you think these are obvious, I think that is okay.